All right, so now we're on to chapter 8. So we're going to be talking about frameworks. So, so a framework is a set of cooperating classes that's there to structure whatever is common to a problem domain so that programmers don't have to learn the intricacies of the problem domain. They can focus on whatever it is that they uniquely contribute. So as an example, Swing is a GUI framework. It's a framework for building graphical user interfaces that are cross-platform. And so the people who wrote Swing, they know all sorts of stuff that you and I don't know about how to make shapes and buttons and deal with graphics cards and whatever. So then when we use Swing to produce an application, we add in our own stuff. I wrote an application that makes UML editing. I know people who write applications on top of Swing that are there to control railroad signals and moving trains and stuff. So they don't have to know about how to make buttons and sliders appear on the screen. They worry about their expertise, and so they get to use these frameworks. So it's important that you understand that a framework is not the same thing as a design pattern. A design pattern is a good thing, and the framework is a good thing, but they're just entirely different things. Of course, a typical framework such as Swing will use more than one design pattern. You've seen already 5 or 6 design patterns where I said this is a design pattern that occurs in Swing. For example, there's the decorator design pattern with scroll bars. There is the the observer design pattern that Swing uses when it does listeners to buttons. There's the composite design pattern that Swing uses when it does containers and components. So now we want to study frameworks a little bit more. The ones that you're most likely going to run into are called application frameworks. So an application framework gives you everything that one needs to build an application so that the person who does the application building doesn't have to know too much about the basics. So if you think of a bunch of, Windows applications, and think of what Windows applications are there. I don't know. I don't use Windows. What's an application they use? Like Microsoft Word and Internet Explorer and those things. They have a certain amount of things in common, right? They all have menu bars, for example. They all have file open menus and stuff. And the way Microsoft builds them is they have an application framework that factors out a lot of the common stuff that every application has to have. Opening and saving files, for example, putting menus up there, putting toolbars and all of that good stuff. And so they give you a framework where when you launch that framework, you kind of get a shell application that doesn't do anything, but it does have windows and menus and file open and file save dialogues and that kind of stuff. So that way, you as the application programmer don't have to worry about that. What you're more likely to see these days is web application frameworks, where someone has packaged the basic control flow of a web application so that you don't have to worry about the low-level protocol details. And we'll see one of them in the lab today. So one of the things that's characteristic of an application framework is that when you put together an application, say a Swing application or a web application, you're not really in control. When you write a program from scratch, you're kind of particularly like a console program, you're in control. You start with main, you put a message on the screen that says that asks the user to do something. You read the user input, then you do something. Your program controls the event flow. And when you work with an application framework, since you only supply a few classes at the edges, the methods of your classes get called when the framework thinks it's a good idea to call them. So that's what's called inversion of control. Sometimes it's called the Hollywood principle, because don't call us, we'll call you. So the framework will call your methods when appropriate, and you just have to have that way of thinking. When this first started out, I remember 30 years ago, this was something that bothered programmers greatly, that they felt that they lost a lot of control that way, and they had to be able to always react to things that happen. Nowadays, we've been doing this for a long time, and it's a much more understandable thing. So those of you who've been doing the Android application, you're fully aware of that you get called once in a while and you have to react to those circumstances. So as an example of a simple framework, I thought I'd give you something that's like JUnit, Because JUnit itself is a framework, and then we'll dumb it down just a little bit so that we can see how a framework might look inside. So good old JUnit, when you have test cases, you put up a class for testing, then you have methods that are annotated with @test, here and here, and whenever you have one of those methods with this annotation, then the unit test framework will call it. See, that's again inversion of control, that the framework is in control when it calls the various test methods. What else does the framework do for you? It collects the results. It prints a little report of the results. If you use one kind of runner, it just puts a little thing at the bottom in text on the screen. If you use a different kind of runner like the one that's in Eclipse, you might get the green bar and all of that kind of stuff. You, the user of the framework, don't care about any of that stuff. You never have to worry about how to collect a report and analyze results. So that's inversion of control. So you can even see that when you invoke JUnit, remember how to do it. You say, look for me today. So you just say Java dash class path, and what do you give? You give the class path of the JUnit libraries, and then the class that you're running is JUnit.runner.JUnit_core. That's the class that contains main. You didn't write that class. It calls the methods in the class that you then give as a command line argument, the daytest. All right, so let's say we wanted to build something like this. That's a little bit easier to understand, just so that we understand how one might build a framework. So JUnit uses these annotations. We don't know anything about how to use annotations, so we're not going to do that. Instead, we're going to say we'll be object-oriented. We'll say that every test case has to extend a common class. Rather than making a test case a method, we make each test case into a class. The common class here is the one that I have here. And it has a single method called execute. That's a method that we override. And so that's a little nicer from a design perspective maybe than in JUnit, even though it's not quite as convenient for the user, because now we know what the method is called. It's always going to be called execute. Whereas in JUnit, they were annotated, and someone had to find out which methods were annotated by using reflection. So here we can simply, in the framework code, this is something that the framework writer worries about, we call execute, so we execute a test case, and then we report on the success if it passed, meaning it came back without an exception, or if there was an exception, then we report some failure. So the code that you see over here, this is all the code of the framework, not the one that the author of test cases has to provide. So in JUnit, when you write the test case, you write a few statements, and then you want to assert something. And so we'll do the same thing in our mini framework here. Because they're always called an execute, and that execute is inside test case, we can put these assert methods just inside the test case class. In JUnit, they're separately. Remember, you always have to do a static import to get them. But here we can actually do this very simply. So here I wrote one of them, assert equals, and it just checks whether the two objects that are passed are equal, using objects that equals. And if not, then it throws some exception. I just make a separate exception so that I'm not standing in the way of any exceptions that might naturally be thrown. So that's all good. Now, as the designer of the framework, I still have one problem. I need to know what test cases should I run. The user of the framework will supply some number of classes for test cases. And so I'm pushing this a little bit back. I'm saying the user should also give me a class that extends this class called test suite. Test suite has one responsibility, namely to give me all the test cases. So there's a method here called getTestCases that returns an array of test cases. And that has to be overridden by whoever wants to run the test. Now that once I have the test cases, then I can implement this run method. And here it is. So this is now my main method. This is the method that is part of the framework that's not inside what the user supplies. It goes through each of the command line arguments, and each of those command line arguments must be the name of a test suite. Remember, a test suite is something that has a method gets test cases where it can get the various test cases. Then for each test suite, I now use reflection to make an instance of that. And I've been thinking about whether there's any good way of avoiding the reflection, but there really isn't, because just like in JUnit, one has to be able to do this with any kind of test classes, and those test classes did not yet exist. I have to load them somehow. So I have to somehow dynamically load them, and that's the way to do that is with reflection. So I say, okay, I want to have the class whose name was given in the command line. I then call a new instance on it, and that way I get an object of that class. Then I call the run method on it, which I know exists on the test suite. That's the method that you've seen on the previous slide that runs through all of the test cases. So it calls get test cases, which must then deliver the set of test cases, and then it prints out all of the results. So that's what it does, and it's kind of so it's a few classes. You can see them in the book code. And here is what you would have to do to use them. In Chapter 3, we had an example of a JUnit test run where there were several methods that all did something with days. And so here's one of them. There's a test add method. Previously was a test add method. Now I'm making that into a test add class. The class implements this test case thing here. I override execute. And then inside here, I just have the regular old test that I had before. I didn't even think about it anymore. It does what? It adds 2 days, and it adds some days, and does dates from whatever it does. So previously I had a JUnit class with 4 methods. Now I have to turn that into 4 different test classes, and then I have to make a suite. And the only thing the suite needs to report is an array that has these 4 objects. I could have done this one with reflection as well, but then the command line would have gone very long, so I figured the suite was some value. So that's it. That's how one can make oneself a JUnit like framework. And so there's not much to it, like I said. The basic idea is that the user of the framework supplies some amount of stuff, not worrying about the control flow, not worrying about the thing that's common for all test runs, and the designer of the framework, the one who put together the code that you saw on these slides here, they worry about how to put the common mechanics. So in the book there's now a section on the collections framework that explains why Java util, the various collections, why they form a framework, and how they allow you to add new classes, new collection classes into the framework. And I'm not really going to take the time right now to do that, because it's not a very common thing for programmers to add their own collection classes. And there's a perfectly good set of collection classes, and we don't really need to worry about that. So in the interest of time, I thought it'd be more interesting to skip past that thing and do something more useful. Next time, we're going to be talking about this graph editor framework that you're all using, that Violet is based on. So I'll give just the basic idea, and then we'll move on to the lab. So there's lots of applications where potentially you might want to draw graphs. Violet is just one example. And I had one time I actually had a whole bunch of different projects where students had to put the graph editor framework to work to produce some application that drew something other than UML graphs. And so there was one group that did flowchart, one group that did circuit diagrams, with transistors or AND gates or some such stuff, and one group who did something with floor planning, where there were chairs and benches and tables that could be moved around. I don't remember the details. But you can see that doing any of those things, there's a lot of commonality, right? You have to drag and drop nodes. You have to draw lines and connectors and that kind of stuff. And so the graph editor framework that's in the book in its most basic form, it does all of these things. It teaches you how one can manage that. So in order to make the next lesson effective, what I would like you to do is to at least have a look at this stuff at home, so that when I go through this, that you're not seeing it absolutely for the first time. So so go through that, and then I will try to dig into some of the details. I mean, it should be of interest to all of you, because you're going to be able to use what you learn here in your project. That reminds me of one thing in the project. I noticed there were a couple of people who seemed to have wanted to reinvent the entire wheel and just didn't make use of any of the Violet classes. So if your project is among those, I would question that decision. So that's, of course, most likely to happen with the ones who are not making a swing application, like the FX and the Android folks. Think about how much of the existing framework you can use, because it took me more than 4 weeks to write this framework. So there's probably more than 4 weeks of knowledge in there, or maybe I code slower than you. All right, so having said that, I want to get into the lab because the lab is a little bit tricky. So the idea of the lab is to get you into a kind of an application framework that you're pretty likely going to use at some point in your life. Namely, to write web applications. So I hope you all did this and are at the step that you have this basic naked project in Eclipse. And what it is a web application. So, okay. So when we run this, okay, well, it's slow. So just so that you know what you're seeing, so over here, I started loading it, and at first it said it can't be reached because it hadn't started up yet. Now it says down here, waiting for localhost, and over here, you see it compiling. One of the reasons, so one of the things that this play thing does is it tries to make it so that you can keep developing and testing it at the same time. If you've ever done development with something called Java EE, then you'll know that it wasn't like that there. There you had to, or for that matter with Tomcat, if any of you has used Tomcat, there whenever you made a change in your application, you could try to see if you could reload it, but in more than half the time you had to just turn off the application server and reboot it, and then it would finally work. And it was always super frustrating. So the play people, they try to make it so that you have this instant turnaround, and it does work. Once it warms up, it works pretty well. All right, and now it says welcome to Play, and it gives you this demo page. The other reason that I like Play is that, so now I'm going to put in something where I'm going to make some mistake. I'm going to go to localhost 9000/Fred, and now I get, it says action not found. And not only does it say action not found, which gives me some amount of hint, it tells me what it's trying, it tells me what it tried. Whereas when you do this thing with Java EE, what you get is what's called the stack trace from hell. You get some very long stack trace where you have no idea what you did wrong. So play is pretty nice in that it's programmer friendly. So just a little bit of what goes on with these applications before I let you loose on the lab. Let's see if I can draw. So you realize, of course, that the browser runs on your machine. There's the internet, the series of tubes, and then there is the server, which runs normally on some virtual machine wherever Amazon or Google want to put it. And in our testing setup, yeah, they run on the same machine, but in reality, that's not what happens. So now the browser here makes requests to the server, and then the server sends stuff back. The requests that the browser makes use a protocol called HTTP. Who knows a little bit about HTTP? A few people. So, for example, when in the browser you write localhost 9000 into the browser bar, and then what the request that the browser is going to send is it's going to send over here a command line that says get slash. So get means it wants to get some contents, and the slash just means you didn't provide anything. When I said localhost 9000 slash Fred, then it said get slash Fred, and this string, the slash or slash Fred, gets sent to the server. What the server does with it, that is completely up to the server. What the play system does is it looks at the request string. It says, okay, it was a get request. There's also some other request types that we're not looking at right now. Then it looks at what is the URL, so it's a slash or slash Fred or something. Then it goes through its routing table and sees which method it should call. That's a common kind of way of doing it. Play does that, Rails does that, which is another web framework based on Ruby. It's a pretty effective way. So there's this mapping from the request URLs to whatever method is that should be executed. So on the way from the browser to the server, the protocol is this HTTP protocol, which basically is a text-based protocol, is a command and a URL, and maybe some extra information. So for those of you who want to use this for the collab file thing, you can just use the protocol pretty well, and you'll see after today's lesson quite a bit better as to what you can do. So anything where we want to get something, we call get. We're going to abuse this thing today, and even if we want to put something onto the server, we'll also call it get. So we want to put some scores on it, and we'll say get, and then some command that I can't remember. It's in the lab, and then because all we care is that we have a command from the browser to the server. Now the server has to send stuff back. So over here, the server sent us some stuff back, like here, and so this format was, of course, good old HTML. So here is HTML. And that is if you want to view stuff in a browser. But more often than not, when you write a program in this day and age, what comes back is not for view in a browser, but it's for view in either a phone, which then translates it to the phone, whatever it needs to require to show it up on the phone UI, or it is that there's actually some JavaScript running inside the browser that makes the HTTP requests. Information comes back not directly to the browser, but to the JavaScript, and then the JavaScript is used to update what the user sees in the browser. So a typical web application nowadays no longer sends back HTML, because why would it send back HTML? It's a web application. It's not just a server. It doesn't serve just pages. But it serves it back in something that the client can understand. That could be XML, that could be JSON, or in our case, we're just going to make it send back plain text. So you're going to be seeing plain text in this example. And then you could assume that there would be some kind of an application that makes these requests. That is not actually the browser, but still you make the GET requests to get through the server, and you get text back, whatever the server wants to say. All right, having said that, that should give you enough of an idea to go through the lab. And when things don't work out, let me know, and I'll have a peek at your system.